Alright, hello everyone, my name is Joshua.
I'm Amanda.
And we'll be presenting to you today the x64 processor. So today's agenda we'll be going over the purpose of the processor, the processor overview, which will be over the baseline and enhancements of it. Then we'll go over the structural diagrams. We have a few diagrams of how the processor is built up. And then we'll go into detail talking about the two enhancements that we majorly worked on, which was the barrel shifter and rotator, as well as the multiply accumulate unit, or the MAC unit. And then we'll go over future enhancements, and then we'll close up.
Okay, so what exactly is the x64 processor? It's geared towards digital signal processing, so all of our enhancements make our processor capable of converting analog signals.
So what exactly is digital signal processing? Well, digital signal processing deals with transferring from analog signals to digital and then transferring it back into analog. And this is used in a variety of different fields such as audio encoding and decoding, also in other types of visual media and stuff like that. And the idea for a digital signal processor is to be optimized for conducting numeric calculations as fast as possible. And here's a general diagram of how a digital signal processor works. So it takes an analog signal. This would be created from an I/O port, and it'll be transferred into a digital signal, which will be a series of zeros and ones. And then it'll go through a digital signal processor, which will calculate and manipulate the data, and it'll transfer back into an analog signal, sending to an output.
Okay, so these are some of the baseline features. So we have a integer and a floating point data path, each with their own set of 32 64-bit registers, and we also have the capability to reset and interrupt from I/O.
And a few more highlights of the baseline. We have several different data types. We have a single, double, and triple word, which we define word as a 32-bit value, signed integer, as well as a floating point. We have a program counter and the stack pointer floating within our execution unit. You'll see that in the diagram later on. We also have something known as the X register, which is used for an exchange instruction. You'll also see that later on in the integer data path module. And we also have the capability of interrupt or returning from the interrupt by pushing both the flags and the program counter. And in total, we have a number of 76 baseline instructions in this processor.
Can you hold it right there? Single signed integer. That's in the baseline?
Yeah, this is for, I believe that would be for actually immediate.
Immediate. We have a 32-bit immediate?
No, we do not. No, I'm sorry.
In the baseline. What's a triple word?
Triple word that is used
96 bit?
Yes, 96-bit. This is going to be inside of our accumulate register, which is inside of our MAC unit, which we'll go into detail.
Okay, that's an enhancement then, right?
Yes.
Okay, because this says baseline.
Oh, right.
So baseline just had 64-bit integer.
Right, yeah.
But you're setting a new baseline. That's what's going on. Okay. Setting the bar higher. Okay.
Exactly.
Okay, so our enhancements implemented in the x64. So our two main enhancements are the barrel shifter slash rotator, which does a shift for 64 bits, and we also created a multiply and accumulate unit. And within that, we have an accumulator register that is 96 bits wide, and the reasoning for that we'll explain in a little bit. So we added a few more instructions with these enhancements, 16 new instructions. And so our grand total is now 92 total instructions. And
now this is going to be going over the structural diagrams of the image. So this is the overall processor itself. As you can see, we have the control unit from the side, and this is the execution unit in the yellow box. And we have the I/O and memory. We have the program counter, stack pointer, and the flags register contained within the execution unit because we felt it was best singled out amongst all the other different modules. This is a close-up of the execution unit, which you can see right here. We have a floating point, multiply, accumulate unit, and integer data path, as well as a bus interface unit. Okay, so this is our floating point data path. So it just consists of a register file, our ALU, and a MUX that has the capability to select, get a value from the read buff in our PIU. And this is our MAC. We're just going to go a quick overview of it. Josh will go into more detail in a few minutes. So it just also consists of a register file, a multiplier, an adder, and an accumulator.
Our integer data path, it's basically just like our floating point except for it deals with integer numbers. So register file, we have a mux ALU, and then this also gets a value from the read buff in the PIU.
And this is the bus interface unit. This also contains some of the information, enhancements that we have done for our enhancements. As you can see, we have a floating point buffers as well as a write buff registers. The write buff registers has a mux to incorporate certain instructions that we need to have conducted. The MAR register, which is used for addressing for I/O and both memory, also has a mux that selects from different places from our processor. And we also have 3 registers named mbuff2, mbuff1, and mbuff0, which come from the Mac unit. And we'll go into later detail with that later as well. We also have an instruction register, which will take any instructions when we're reading things from program memory. And that'll also handle sign extension. And we also have 2 read buff registers that will read information from I/O and memory.
Okay, so I'm going to go over our barrel shifter / rotator. So the barrel shifter rotator takes a 64-bit value, shifts it up to 63, shifts or rotates it up to 63 times in one instruction, and it increases performance by saving time. So what happens in the worst case, you want to shift something 63 times. You would have to do 63 shift left or shift right instructions. Instead, with the barrel shifter, it's just one instruction. So without the barrel shifter, you take 63 instructions and 3 clock cycles per instruction. So fetch, decode, and execute. That would take 189 clock cycles total. With the barrel shifter, it's only one instruction, and it also takes 3 clocks, and it'll take a total of 3 clock cycles. So you actually save 186 clock cycles. But in cases that are less extreme, even if you wanted to shift 2 times, for example, you'd have half as many clock cycles. So 2 times it would take 6 clock cycles without the barrel shifter. With the barrel shifter, it'd only take 3.
Mm-hmm.
So this is our some of the instructions that we added for our barrel shifter. This is the instruction format here. So it looks a lot like our 3 opcode one. We have, our 3 operand. So we have the opcode, we have source 1 register, and instead of having a source 2 register, we have a 6-bit shift amount or rotate amount. And then we have a destination register, which could be a different register or the same one that you want to store back into. So this is an overview. Here are the control unit opcodes that we added to our CU, and then this is the ALU opcodes because we did put our shifter straight into our ALU. Okay, so I'll start off with the barrel shift right logic. So it behaves similarly like our baseline shift right logical. So zeros are shifted in, and then the least significant bits are lost. This is the implementation for it. So you'll see in the next slide a bunch of muxes. So it's just a conditional statement, and the shift amount determines how many times the value is being shifted left or right. Okay, so here's our diagram. As you can see, it's 3 rows of 8 muxes, and just for this presentation, we used an 8-bit shifter instead of 64-bit, just for an example. But the 64-bit would be the same way. Instead of having 3 rows of muxes, we would have 6 rows of muxes and 64 bits. 64 muxes across. So go ahead and click on an example. Okay, so for example, let's say we want to shift a value 5 times. So the shift amount would be 101 in binary. And the way it works is the shift amount actually acts as a select for the muxes. So the shift amount 2, the most significant bit of the shift amount here, actually selects 1 for this entire row. So it shifts the value 4 times. So you can see the 0 here, it's shifting in 4 zeros. And then these 4 are being shifted over here. And then it drops down to the next row of muxes, and it'll take the next bit in the shift amount, and that will be the select for this row.
Mm-hmm.
So since this is 0, we don't want to shift it in this row. So it'll just drop down. It'll keep those values, drop down to the next row. And here it's a 1, as you can see up there, and so it gets shifted 1 time, shifting in a 0 right here. Okay, and then the shift left logical works pretty much the same way, except it's shifting left, just like our baseline. And here's the implementation for it. As you can see, it's really similar, it's just a few conditional statements. And this is a diagram for it. It's pretty much the same. The wiring is a little bit different. It's going the other direction, but the concept is the same. Okay, so for our arithmetic, barrel shift arithmetic, it behaves like the baseline arithmetic shift, except it can shift multiple times. So our baseline, we can shift it one time, multiplying the value by 2. For ours, we can multiply by 2, 4, and multiples of 2, basically. So zeros are being shifted in, and the sign bit remains unchanged. So you keep the sign bit and you shift everything else to the left. And this is the implementation for it. It's a little more complicated, but still the same concept. So here's our diagram for it. And as you can see, the sign bit here is kept, so it doesn't go through any muxes. It remains unchanged. For our shift right arithmetic, all the bits are shifted to the right, and instead of shifting in a 0, we're going to shift in the most significant bit. It affects the negative and 0 flags, and the implementation, as you see, is similar to the others, and you're keeping the most significant bit to be shifted in. Okay, and then here's the diagram of it. As you can see, what differs between this and the other diagram is there's no 0, so you're not shifting in a 0, you're shifting in whatever was in R7. Okay, and then here are our rotates. This is our barrel rotate left, and it works just like a rotate left. Here's the implementation for it, and we'll go over an example in just a second. Okay, so this is the diagram for it, and in our example, we want to rotate it 3 times. So here, similarly to the example we gave you on the shifts, this remains unchanged, so the values are just dropped through the first level of muxes. On the second level, the bit is a 1. So the select is a 1, and everything is shifted over, rotated twice, and then it drops down to the next level, and it's rotated 1 more time. And then this is our rotate right, similar things, and this is the diagram for it. It looks a lot like the rotate left. Actually, the first level is exactly the same, because when you do a rotate left, for 8-bit, you would rotate left 4 times or rotate right 4 times. It's the exact same thing. So Josh is going to go ahead and take over for the Mac.
Thank you, Amanda.
Before you go on to that, since we're in context,
Right.
so your implementation was not instantiation of a bunch of muxes. You just let Verilog do that for you? So in other words, your implementation showed Verilog
It's just
conditional
like
assignment
concatenation.
statements.
Yeah.
So you let the synthesizer create the muxing.
Right.
And then you just decomposed it to show us kind of how it
This is
works,
how it works. Yeah.
which is always a hard job. I don't know how many really could get it, but you did a good job, Amanda, because that's usually, it takes time to think about really what's going on. Good job.
This is our second major enhancement, which is the multiply accumulate unit, or the MAC unit. And what the MAC unit essentially does for our purposes is 2 fundamental operations, which is a multiply and as well as an addition. The MAC also has a 96-bit register known as the accumulator, and what this will do is it will store the results of a multiplication of 2 single-word operands, and we'll go over how that works in just a minute. The MAC will also conduct an accumulator version of these multiplications, so either it will store directly into the accumulator, or it will add the contents of the current accumulator into as well with the results of the multiply. Thus the name accumulate, it will just increase the value of it. With the size of the register being 96-bit, we give ourselves a 32-bit, you can say as a cushion to ensure that we do not go over wraparound. Technically we can still go over wraparound, but it would need to reach 2 to the 63rd minus 1 divided by 2, which is a very large number. And we do handle it in our code though. So this is the diagram once again for the Mac. We'll be going over this in a little bit more detail. Now from the register file, we have 2 values, R and S, which are 64-bit values, and we have something known as the M muxes, which will select whether or not we want to choose which of the upper or lower part of the 64 to multiply. So with these 2 muxes, we're able to choose either we want to multiply both the lower parts of the 64-bit operands, or we can choose to multiply both the upper, or we can choose a mixture of either the lower and the upper parts. Both operands are put through the multiplier, so 32 times 32 will make 64 bits, and it will pass through this mux right here, and then go through the adder and go into the accumulator. This will be for any of the multiply instructions that we have that go with our multiply accumulate unit. If in terms of multiplying and accumulating, it'll go through the same process, choose whether which 32-bit operands to select from to multiply with. It will pass through that mux, and it will go into the adder, and the adder result will now be an operand in that adder, so it will add both the current contents of the accumulator as well as the results of the multiply. The reason why we have an adder in mux was for a feature enhancement that we did not unfortunately get working in time.
Which was?
It was a clear for the accumulator, which would just zero out the accumulator and just start from scratch. Now we have also a few more instructions, which is load and store for the Mac. We have a loading from memory, which will take the contents of 2 memory registers pointed to by an integer register in the ALU, and will put it into a register in the register file of the Mac. The Mac unit also contains the same size register as the floating point integer, so it's going to operate as very, very similar to the load and of the floating point and the integer data paths. Thus, at the end of the last state, it would go into the Mac instead of one of the other ones. Storing is very similar to as well as to the integer and as well as the floating point. However, instead we have a 96-bit accumulator register that's going to be going into memory. So what we do is we split it up into 3 different registers in the bus interface unit. And then from there we store each one into memory one at a time. So we have 3 registers instead of 2, adding one more state to the compared to integer and floating point storing. And we store all of those information into little endian format. So here's a diagram of how the process will work. So this is going to be general for loading and storing. And this is going to be the pathway. The highlighted part in blue will be the path of a load. So we'll go into the data bus, go through the read buff, and then go into the register file within the Mac. And this is for the Mac store, which will come from the accumulator into the 3 registers of the BIU, and then from there each one will be sent out into memory. And here is the implementation of our code in Verilog.
Okay, so future enhancements. We're looking into creating a load immediate instruction. So similar to our baseline load immediate, we want a load immediate that goes into the register file of the Mac unit. And then we want load and store instructions from the I/O into Mac instead of just from memory to the Mac.
And now we also have 2 other instructions, an I/O to memory and a memory to I/O. And what this would be is it would be an extra input wire that would be going into the bus interface unit. We would create a register within the bus interface unit that will be 32 bits wide and will hold the temporary value of a value from either coming from I/O, and then in the next clock tick it would go into memory, or it would come from memory, go into that intermediate register, and then go into I/O.
How do you hold the 2 different addresses?
Oh, that would be pointed to by the address. So this would be
There's a memory address and then an I/O address.
right. So we would have 2 different registers that would integer registers. I'm sorry, that would select whether or not we would want to go from. We'll select what we want from the I/O, and then the next one would select the.
So the instruction itself would have codes for the 2 registers to use,
Yes.
as well as, okay.
We also would like to implement a bit reverse addressing mode. We were doing a little research online, and there is a lot of different algorithms that are used with the Mac processor. One of them being a fast Fourier transform algorithm.
Okay, and what it does is basically it goes through a loop, and it does whatever manipulation, arithmetic, or changes to the actual value, and the output is the address in reverse. So with the bit address reversing mode, we just reverse that and use it as an address.
And we also wanted to eventually create a pipeline version of this product. Right now it's currently in a von Neumann architecture, which makes use of only one memory module. What we would like to do in the future would be create a Harvard architecture, which splits the memory into two different memory modules, which would be program memory and data memory. That way we would be able to create a lot more streamlined product.
Mm-hmm.
And in addition to that, since we are using Harvard, we'd have to add an additional bus.
And do I have any other questions?
Did I see a way to load that accumulator with a value for the Mac instructions?
Unfortunately, we do not have one that loads directly into the accumulator.
So how would you do
The
that?
process would require a person having to load into a register within the register file of the Mac
First, and then drop it in?
Yeah.
and then drop it in.
What's the drop-in instruction?
We
We
haven't
haven't
created an instruction for that, so that would also be a further instruction that we would have to plan
So
out.
how did you verify that the Mac, the multiply and accumulate worked?
Well, we created a test bench inside of the memory module, and what we did was we tested what the value of the accumulator was in the beginning, which was 0 or x, because there was nothing loaded into there. And then we would conduct a multiply instruction that is geared just for the Mac. And what that would do is store directly into the accumulator.
Okay,
and
that's
then
how,
check
that's
for
how
that.
you loaded it?
Yeah.
Okay.
Any other questions?
What's the difference between your multiply and accumulate and Bruno and Bo's multiply and accumulate?
Well, our multiply accumulate is of a more, I believe, scalar. That would be more of a correct term to say.
In other words, you know what theirs did, right?
Uh,
You weren't paying attention?
Little paper over here.
No, they did 2 multiplies and added the products together,
Right,
whereas this is
right.
more of a DSP implementation that the
Because it's
filtering
accumulating
user-
rather than just
Right.
getting two values and adding them together.
Yeah,
Right.
yeah.
So ours is we're combining the results of a previous accumulate as to a multiply result versus the previous presenters who have 2 multiplies that and add those together.
Here's a loaded question. Whose is better? Oh.
Depends on the application.
Which
Well,
was
there's-
what I tried
there's-
to ask them, what's the application? You know, what's that used for versus what's that's for?
Well, there's nothing wrong with the previous presenter's version of
Very, very political.
However, with ours, we have the ability to use data from the past and implement it into the new one. From the previous presenter, they would need to have the operations being done at one time and handle it there. While we can have an instruction that would manipulate the data beforehand, and then we can continuously loop, making it easier on the program as well.
For the sake of everybody, it's all a matter of applications that use the different instructions. It's not a matter of better. Any other questions?
You guys had 16 enhanced instructions, right?
Yes.
I think you guys only went over like 6. What were the other 10?
The other 10 are inside of the Mac unit, which is, there's about 4 different versions of the multiply, which we can do a multiply with the lower bits of the operands of the 64, we get the 32 bits. And we also have so we have a dance of a sort of like a low, 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 high, high, low, high, high. And as well as we have an accumulate version, which will do the multiply of the low, 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 high, high, low, and high, high, and as well as add it with the accumulator value, so it's a little bit of that.
Excellent. Thank you very much.